Welcome to qnawire.
Hi, so over here we're given the dissociation of a mystery acid, which is going to have a value for delta G standard at 25 degrees Celsius equal to 30.3 kilojoules. With this, for the first thing that we need to know is this a strong or weak acid? So over here we can directly say that this is going to be a weak acid since the dissociation is not going to be spontaneous, and in order to identify this, we are going to say that delta G is equal to delta G naught plus RT logarithm of Q. This is going to be the general equation for the dependence of delta G with Q and temperature. So at equilibrium, oops, the value for delta G needs to be equal to 0. So that implies that delta G naught is equal to minus RT logarithm of K. In this case, also, at equilibrium, Q is going to be equal to the equilibrium constant. And in particular, since we're dealing with an acid, this is going to be the logarithm of Ka. So, from here, we know that Ka is going to be equal to the exponential of minus delta G naught divided by RT. So, this is going to become exponential of minus 30,300 joules. In this case, we need to convert kilojoules to joules, divided by R, which is 8.314 joule per mole Kelvin, times the temperature, which is 25 degrees Celsius, which corresponds to 298 Kelvin. Thus, the value for Ka would be equal to approximately e to the minus 12.23, which is equal to 4.883 times 10 to the minus 6. As a result, we can say that the pKa, which is the logarithm of this value, well, minus the logarithm of the value for Ka, would be equal to 5.3113. So, as you can see, the Ka is positive, thus larger than 0, thus, the pKa is larger than 0, thus we're going to have a weak acid. So with this, we have answered part A of the question. Now, let's go with part B. We want to know what is going to be the value for Q when the change of delta G is equal to 40.5 kilojoules. So, in this case, since the change of G is equal to 40.5 kilojoules, we're going to use the full equation. Delta G is equal to delta G naught plus RT logarithm of Q. Solving for Q, we're going to get that delta G minus delta G naught divided by RT would be equal to the logarithm of Q. Thus Q is equal to the exponential of this value, delta G minus delta G naught divided by R times T. Replacing the values, Q is equal to the exponential delta G, 40.5 kilojoules, which is 40,500 joules, minus delta G naught, which is 30,300 joules, divided by 8.314 joule per mole Kelvin, times the temperature of 298 Kelvin. The temperature is going to be kept constant, so that we are still under standard conditions, and the value for Q is equal to 61.37. 3708 if you want to use more significant units. So that means that since the value for Q is going to be much larger than the value for the equilibrium constant from Ka, that means that the reaction is going to go towards the left, meaning that the dissociation, let me exemplify this in a much more clear way, that the reverse reaction on the production of H2O plus A minus is going to be much more favored in this scenario. And of course, we're missing here water. Water plus HA, giving this. Okay, so is this reaction at equilibrium? No, not at equilibrium. The reaction would be at equilibrium only if the value for delta G is equal to 0. And this reaction is going to be under standard conditions since we are going to still have the values for pressure and temperature required for that. And finally, for part C, we want to determine the value for delta G when delta G equal to unknown, when the concentration of the weak acid is equal to 1.8 times 10 to the minus 5, the concentration of H2O plus or of H plus is equal to the concentration of X minus, I assume over here that there is a typo on the question, is equal to 2.3 times 10 to the minus 3. So, under these conditions, the value for Q would be equal to the concentration of H2O plus times the concentration of X minus divided by the concentration of HA. Remember that water doesn't enter into any equilibrium calculations since it is going to be a solvent which is in a condensed phase and the activity associated to that is equal to 1. So over here, what we're going to get is 2.3 times 10 to the minus 3 squared, since both of the quantities are the same, divided by 1.8 times 10 to the minus 5, which gives us a value of Q equal to 0.2939, keeping up to 3 significant digits. The actual result is 2938, 8 periodic. And now with this, we want to calculate the value for delta G. So what we're going to get is directly delta G is equal to delta G naught plus RT logarithm of Q. Delta G naught was 30,300 joule per mole plus RT, which is 8.314 joule per mole Kelvin, times the temperature of 298 Kelvin. Remember, the temperature hasn't changed. And all of this multiplied by the logarithm of Q, 0.2939 approximately. So the result that we're going to get is delta G equal to 27,266.08 joules per mole. Reading in kilojoules, it would be equal to 27.27, rounded up to 4 significant digits, kilojoules per mole. So again, what this is going to indicate is that since delta G is lower than the value for delta G naught, that means that to achieve equilibrium, the reaction is going to be shifted towards the right. Oh, sorry about that. In this case, it is not related to delta G, sorry about that. Since the value for Q is going to be still larger than the value for the Ka to achieve equilibrium, the reaction is going to be shifted towards the left. And this is going to be because delta G is still larger than 0. So to go to 0, delta G equal to 0, which implies equilibrium, the reaction should go towards the left, meaning we're going to generate more of the weak acid. And with that, it would be all. Thank you very much. Sorry about the small confusion from before. And with that, it would be all. Thanks and have a good one.